Okay. In one of the last videos, we spoke about sequences in general, and you can have any kind of sequence. Let me start with an example 0, um, and consider the sequence 0, 1, 2, 0, 1, 2, 0, 1, 2, and so forth. So this is a perfectly good sequence. The 100th element is going to be 0, and so forth. Um, and it is a sequence as any other. And you can have sequences not just of numbers, you can have sequences of things, items, days of the week. You can start with Sunday, Monday, Tuesday, Wednesday, Thursday, Friday, Saturday, and then Sunday again. Those are cyclical sequences. So there's all kinds of sequences. You can have the sequence of the digits of pi. So for instance, so this is just one example. I guess example 1. You can have 3, which is the first digit of pi, and then 1, 4, 1, 5. I haven't memorized them, so 14, 15, 9, 2, etc. So that could be a sequence. If you just take them apart, each one of the digits of pi, then you have a sequence. So there are many kinds of sequences, and this is a little bit of a random sequence. This is almost exactly the opposite of random. This is very predictable. We know exactly what each element will be in each moment. You can have you can take a coin, say this coin, and flip it, and every time you flip it, you record whether you have, so another example could be, again, you flip a coin, and every time you flip it, you record the output. Let's say the first time it's heads, the second time it's heads, and then tails, and then heads again, and then tails and heads, and you keep doing this indefinitely. Well, that's a very good sequence. It's a very random sequence because the output is completely unpredictable. Even if we go through a streak of many heads, 10 heads in a row, nothing tells us what the next one will be. The probability that we'll have a tail or a head on the next tossing of the coin will be still 50%. So that is totally random. If you ask me what would be the next one, my honest answer will be, I don't know. There's a 50-50 chance that it will be one or the other. If you tell me which one the next number will be, again, I will have to look it up. I don't know. But at least there are places where I can look it up. This one is completely predictable. So there's all kinds of sequences. There's the Fibonacci sequence, that starts with 1, 1, and then the next term is the sum of those two, and then the next term would be the sum of those two, which is 3, and then you add those two to get the next one, 5, and then you add those two to get the next one, and so forth. So that's another kind. Is this predictable? Well, I'm not going to answer that question, but anyway, so that's the Fibonacci sequence, and there's all kinds of sequence. We're going to narrow our view. We're going to focus on arithmetic sequences. Arithmetic sequences are very, very special. And then once we do that, then we're going to move on to geometric sequences. So an arithmetic sequence, let me start with an example. It's going to look like this. Start with one number, say 5, and then move to another number, say 8. And the thing is that the difference between this one and this one has to remain the same. So the difference between 5 and 8 is 3. So the next element in the sequence has to be 3 units away from 8 in the same direction. So 11. And then 3 units later, 14. And then 3 units later, 17. And then 3 units later, 20. and then 3 units later, 23. Well, you get the idea. So this is what is called an arithmetic sequence. You can figure out the arithmetic sequence if you know the first element, which we will label from now on as A, is our first element. And the difference, which is going to be the same no matter what, will be called D. D is the difference. Okay, so I'm going to copy this sequence again. So this is still example 4. Okay, so again, we start with 5, 8, 11, 14, 17, 20, and so forth. That's an arithmetic sequence. The first element, which we label A as A, is 5. The difference is positive 3. By the way, a sequence could have a negative difference, and it could have a negative number. Now, so A1 is 5. A2 in the sequence, so this is the A1. A2 is 5 plus 3. A3, which is this guy, is 5 plus 3 plus 3. A4 is 5 plus 3 plus 3 plus 3. And the reason why I'm doing this is because I want to come up with a generic formula. A5 is 5 plus, so this is 1, 2, 3, 4, 5. 17 is 5 plus 1, 3, 2, 3, 4 threes. So can we come up with a formula for a generic A sub n? Well, all of them start with 5 plus a number of threes. So we're going to multiply by 3. But how many of them? Well, in the fifth element, we have 4 threes that we add on to the 5. In the fourth element, we have 3 elements that we added onto the 5. So 5, 4 threes, 4, 3 threes, 3, 2 threes, 2, 1 3, 1, no 3. So that means that we are adding always 1 less than the index number of threes. So 1 less than the index. The index is, in this generic case, n, so 1 less would be n minus 1. So I'm going to rewrite it because that is kind of squished in there. So n minus 1, close the parenthesis, times 3. There. Okay. So that is the formula. And the formula always is the same. In general, so if you have a sequence A plus D, A plus 2D, A plus 3D, etc. So that's a generic arithmetic sequence. Then the formula will be A sub n is the first guy, which we are labeling as A, plus n minus 1 times the difference. So this is the generic formula we're using for any arithmetic sequence. So in this case, we have 5 as the first term, n minus 1, and 3 is the difference. Now, once we have this sequence, there's a number of things we can ask. We will ask. So for instance, what is the 100th element? Find the 100th element, which of course we label as A100. Well, once we have the generic formula, then which is this one for that particular. So going back to example 4, this is the formula. Well, same as that. If we want the 100th element, A100, all we have to do is add 5 plus n minus 1. So that would be 100 minus 1, 99 times 3. All right, let's do that. So 9 times 3 is 27. We carry 2. 9 times 3 again is 27, and 2 is 29. So we have 297 plus 5, which makes 302. So if back in the sequence you start with the first element, second element, third element, fourth, all the way up to 100, what is the 100th element? Well, instead of going one by one figuring this out, we can use this formula or this formula, and we know the answer will be 302. Start with 5, and then go out by 3s, and we end up with 302. There is something else we want to ask. There is what is called the partial sum, or a partial sum is of a sequence, or in a sequence, is nothing else but sigma of a sub n from n. Sorry, I'm going to change the index. Sigma of a sub I from I equals 1, so the first element plus the second element plus the third, and so forth, up to the nth element. Yeah. And oftentimes, so that's what I call a partial sum. Oftentimes we have a shorthand for this. If the sequence is understood, then this partial sum is labeled as S sub n. It's just a regular S as in Sierra. It's a regular S sub n. And if we have an arithmetic sequence, we have a formula for it. Let me double check my formula. Yeah, it is n times the very first element plus the last element in the sequence, well, in this partial sum that we are adding, all of that divided by 2. Okay, we're still under the same example, by the way. So we are still, wrong spelling, still in example 4, with our sequence, which starts with 5 and 8 and 11 and 14 and 17 and 20. And it keeps going. Okay, let's say we want to find 1, 2, 3, 4, 5, 6, S sub 6, which is really the sum of the elements in the sequence from the first one to the 6th one. So this plus that plus that plus that plus that plus that. Let's do this in 2 ways to make sure we understand what is going on. So the brute force way, I suppose, is just to add them all together. So this sum is really 5 plus 8 plus 11 plus 14 plus 17 plus 20. And I'm going to continue right in here. So one thing I notice is that 5 and 20 is 25. 8 and 17 is also 25. 11 and 14 is 25. So those two together make 25. Those two together make 25. Those two together make 25. So we have 25 times 3. So the answer is 75. That's what we know the answer is if we add the terms one by one. Okay. Or we could use this formula. This formula says 6, we're adding the first 6 elements. 6, in parentheses, the first one, which is 5, plus the last one we want to add in our sequence, 20. And then divide by 2. So we're going to end up with 25 times 6 is 150, divided by 2, 75. Which one is easier, to do it one by one or to use the formula? It depends. In my opinion, it depends. If there are only a few elements, such as 6, maybe even up to 10, we're good. But if the elements are too many, then the formula, of course, will be much better. So for instance, let's say we want to find S sub 100. So that is the sum of the elements from 1 to 100. Okay. Whoa, this is not easy. Of course, I'm not gonna write down 5 plus 8 plus 11 plus 14 plus 17 plus 20, all of the 100 first elements. That would be too much work. So instead, what we do is use this formula. If we want to add all the numbers from 1 to 100, well, the first, how many elements are we adding together? 100. Which one is the first one? 5. Which one is the last one of those numbers we're adding? Well, earlier in example 4, we found the 100th element. Remember, the 100th element is found using this formula, or this formula. So it is 302. 302, and then we divide by 2. See? And then a quick computation, or a couple computations will do this. So that is 5 times, rather, plus 302 is 307. 307, 100, because we're multiplying by 100, but then we have to divide by 2. So 30 divided by 2 is 15, and then 700 divided by 2 is 350. So there we have it. If we add 5 plus 8 plus 11 plus 14, all the way up to 302, which is the 100th term, without having to add all of those terms together, here is the answer. 15,350. Okay. I'm gonna do one more thing. Let's say we want to add all the terms from I equals 7 to 20, something not too far out of the AIs. And we're still in example 4. So we still have the same 5, what is the other one? 8, 11, 14, the same arithmetic sequence. Okay, so the tricky part here is that we are starting with 7. So we're not adding the 5 and the 8, the 11, the 14. No. Figure out what the 7th element is, start there, go all the way up to 20, multiply by, okay. So instead of doing that, I'm gonna do this in like 3 steps. First, I'm gonna find the sum from I equals 1 to 20, starting with 1. So this is S sub 20. Okay. So I'm just going to add all of them, starting with 5 all the way through the 20th term. Oh, I got to find the 20th term first, because the formula calls for 25 plus, but I need to find this number and then divide by 2, but I don't know what this number is. So I'm going to put a little arrow, question mark, and then how do we find that number? Well, we did have a formula. 820 was equal to the first element plus 19 times the difference. Remember? Make sure you know that formula. It's handy. Because one of the basic questions we will ask you is, well, find the 50th element or the 15th element or any element in the sequence. And of course, you're not going to do that one by one. What if we want to ask you for the 1000th element? Well, that's just going to take too long. So we do this computations, 5 plus 57, and that is, of course, 62. So this is 62, and that's it. That is going to give us 67. times 20, whatever that is, divided by 2, 670. Okay, now that is the sum from the first element all the way up to the 20th element. But I don't want to add from the first element to the 20th element. We want to add from the 7th element to the 20th element. So that means we have to take away the first 6 elements. Okay, so S sub 6, which is the sum AI from I equals 1 to 6, is equal to, okay, and we did this earlier, remember? S sub 6, which is the sum of the first 6 elements, we did it in 2 ways. We add them one by one, all the elements, and found out that the sum was 75, or we use the formula. Either way, we know the answer. The answer is 75. Okay, so the sum of the AIs from I equals 7 to 20 will be S20 minus, now don't do S, this is a 7. Don't do S7 because we want to include the 7th term in the answer. We want to exclude everything that is before the 7th element, and that's why we subtract S sub 6. And that is 670 minus 75. So the final answer is 595. There is our answer. So if you add the 7th element, the 8th element, the 9th element, the 10th element, all the way up to the 20th element, here's the answer. And the beauty of this is that I don't even know what the 7th element is. I know the 6th element, I think the 6th element was a 20. Yeah, I'm pretty sure it was a 20. But the 7th element, I guess it would be 23. Yeah. Yep. So 62. I was wondering whether we can modify this formula to find this truncated sum. But I'm not gonna try to figure out that right now. Yeah. And there's a whole bunch of problems we could ask. Yeah, for instance, well, so new example. Okay, so example 5, assume A sub, I don't know, 14 is 20. And A sub 15 is equal to, let's do 27. Okay. So the question is, write the first 5 terms of these of the arithmetic sequence. I guess this is part of the assumption. I should have written it. Assume we have an arithmetic sequence. So that is part of the assumption. If we know that the 14th element is 20 and the 15th element is 27, what are the first few? Well, if we have two numbers that are consecutive, two terms that are consecutive, so there is a bunch of terms, and then eventually we get to 20, comma, and then 27, and then there are more. Well, if we know two that are consecutive, we know the difference very easily. 27 minus 20 is, of course, 7. So we know the difference is 7. So if I want to know the one before, we just go down by 7. So if we start with 20 being the 14th element, if we go down by 7, we have the 13th element, which is, 13, that is a coincidence. I didn't plan that. The 12th element is 7 down from that, 6. The 11th element 7 down from that would be -1. The 10th element, 7 down from that is -8. G. Or I'm trying to think if there's a faster way to do this instead of, because I want to go all the way down to the first element. All right, we do have a formula for the generic a sub nth element. It is the first element plus n minus 1 times the difference. We know the 14th element. The 14th element is 20. This is the 14th element, which is equal to the first element plus. Now, if this is the 14th element, that means that n is 14. 14 minus 1 is 13. And we know the difference is 7. Okay, so we have an equation, and we can figure out what a is from that equation. 20 is equal to a plus 91. And then we can bring the 91 to the other side of the equation by subtracting 91 from both sides of the equation. And then we can put the a on the other side. Anyway, a will be equal to -71. So if we keep doing this, -8, -15, -22, because remember, we're going up by 7. So if we go in the other direction, we're going down by 7. Now I forgot what it was, 15, 22, -22, -29. Eventually, we end up with the first element, which is -71. So if we want to write down the first elements, the first element would be -71. Up by 7, we go -60. I have to think about this. 4, and then -57, and then -50. 1, 2, 3, 4, -43. Well, in this problem, I asked write the first 5 terms, which we just did. But I'm curious. Curiosity within reason is a good thing. 1, 2, 3, 4, 5. If we keep going up, let's see. We're not going to do hundreds, but now I want to keep going up a little more. -30. I'm thinking what it has to be. 36. And then -29. And then -22. And then negative, what is the next term? 15, and then -8, and then -1, and 7 is +6, and 7 is 13, and 7 is 20, and then 21, and then it keeps going like that. So notice that in the original problem, in example 5, the 14th element is 20. Well, sure enough, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13. The 14th element is 20. Oh, I meant to put down 27 here. The 15th element is 27. So they match. So this makes perfect sense. Yeah. So there's a bunch of questions like that we could ask. Now let's up the ante a little bit. What if we ask, okay, so assume a sub I from I equals 1 to infinity, I equals 1 to infinity, is arithmetic. Okay, so we know it has the pattern that we go up or down by the same quantity each from one term to another. Okay, A14 is 20, and let's say a 20, which is a little confusing, I know, is equal to, I'm trying to think of, so 15, 16, 17, 18, 19, 20. Let's just say 30 and see what happens. Okay. So 14, when the input is 14, the output is 20. 15, we don't know. 16, we don't know. 17, we don't know. 18, we don't know. 19, we do not know. 20, a sub 20 is 30. So the question is, what are the ones that are missing? Or even better, what is the difference? Um, Well, I know the big difference. The accumulated difference between this term and this term is 10. That's the accumulated difference. How many times are we adding the difference of the arithmetic sequence to 20 to get up to 30? Well, 1, 2, 3, 4, 5, 6. So we have to add 6 times. So that is equal to 6 times the difference. 10, which is the big difference, is actually the difference once, twice, 3 times, 4 times, 5, 6 times. That means that the difference is 10 divided by 6, which is the same thing as 5/3. Yeah. Oftentimes, the difference is a fraction or a decimal, not a whole number. So if we start with 20 and 5/3, well, 5/3 is the same thing as 1 2/3. So the next term would be 21 2/3. Boy, that gets a little complicated. Then we need to add another 1 2/3. So that's 22, 23 1/3. Oops, 20, let me scratch that, 23 1/3. And then 25, yep. And then 26 2/3. 27, 28 1/3, and sure enough, we end up with 30. So if this is the 14th element, 15th, 16th, 17th, 18th, 19th, 20th. Yep. So we know that the difference is 5/3 or 1 2/3. We typically keep it as 5/3. Another question we can ask is, what is the first element? Well, if we know that the 14th element is 20, that is equal to the first element, which we do not know yet, plus n minus 1. This is the 14th element. So that means that the 13 has to be multiplied by the difference, 5/3. Okay, so that means, okay, anticipating we're going to subtract 20s, rather thirds. I'm going to turn that into 60/3 equals a plus 65/3. So that means that a is negative 5/3. The first element is negative 5/3, which is similar to the difference. That's very coincidental, by the way. That means that we go from negative 5/3 to 0, to 5/3, to 10/3, to 15/3, and so forth. Of course, we simplify, or we can write things as mixed numbers as well. Okay, so there's a whole bunch of questions we can ask. Be prepared, think about those questions. Let's move on to geometric sequences. So at the beginning of the video, I mentioned we're going to deal with arithmetic, now geometric. What is the difference between arithmetic and geometric? By the way, there's a sea of sequences out there. There's all kinds of sequences. We are narrowing things down to only 2 of them, arithmetic and geometric. But there are many, many more. There's tons and tons. There's a whole ocean of sequences. And again, we're going to narrow our focus to only two kinds of them. Yeah, and those are very fruitful, very useful. That's one of the reasons why we're focusing on those two. It isn't just a random thing. There's many applications that use those two, and that's why we're focusing on those two. So geometric sequences. Okay. So the first term is just any number. The next term is a number multiplied with a number, a constant. And then the next one is going to be multiplied again from the previous one. And the next one is multiplied 3 times, and so forth. Well, that is the same thing as AR squared, AR cubed, AR to the 4, and so forth. So we have a geometric sequence. Of an example, which is quite common, example 7, would be 1, 2, 4, 8. So I was going to put down 6, but no, that wouldn't work. 1, 2, 4, 8, 16, 32, 64, etc. So this sequence has a first element. The first element is usually called A, and then we don't look at the difference. We don't subtract to figure out how much the difference is. Well, the difference is 1, but then the difference here is 2, and here the difference is 4. So the difference keeps changing. That causes this sequence not to be arithmetic. In an arithmetic sequence, the difference from one to the next one is constant. It's always the same number. Whatever that number is, it is always the same number. Here, the difference is different, and consequently, this is not arithmetic. But what is the ratio? If we divide 2 by 1, 2 divided by 1 gives us 2. 4 divided by 2, 4 divided by 2 is 2. A divided by 4, A divided by 4 is 2. So if we do that in every element, every consecutive elements, and we end up with the same number, 2, 2, 2, in this case, we have a geometric sequence. That's the test we can see. So what is the formula? The formula for the nth element is the first element, r, to the n minus 1. By the way, in the arithmetic case, a sub n equals a plus, so here we're multiplying, that is a contrast, n minus 1, both use n minus 1, but here we multiply with the difference, and the n minus 1 here is the exponent of the ratio. This guy is called the ratio of this sequence, of the geometric sequence, ratio. 2, and it is the same across the sequence. It is the same ratio. It has to be the same. If we had 2 and another number that is not 2 here on the next one, that's not geometric. It is some sequence, but it's not geometric. Yeah, so this is the formula. So if somebody wants to know what is the 10th element, see, I don't want to go too big because this sequence can get the elements can get too large. For instance, if I use this calculator, yeah, and let me clear this, and I want to put 2 to the, if I want to find the 100th element, just to give you an example, that means the exponent has to be 99. And yeah, I cannot write all the decimals because there's too many decimals. This uses scientific notation already. This is huge, too big to handle. So in this case, finding the 100th element with all of its digits is very, very difficult because we're going to end up with about 30 digits. So that's why I didn't want to do that. So the 10th element, for instance, would be 1, which is our first element, times 2, which is the ratio, to the 9th exponent. And that one we can even do on these calculators, in simple, easy calculators. So 2 times, so that's 2, 3, 4, 5, 6, 7, 8, 9. So 512, 1 times 512, which is, of course, 512 is the 10th element. As with arithmetic sequences, we have a formula for the partial sum. Now remember, partial sum is S sub n. We usually label it as S sub n, which means adding the elements in the sequence from the first one to the nth one. And the formula, I mean, you can do that by adding one by one, or you can apply this formula. S sub n is the first element, whatever it is, times a fraction. The fraction is 1 minus r to the n plus 1 over 1 minus r. There we go. So that is the formula. Some people rewrite it. They distribute the a on the numerator, which is correct. And so a times 1 is a, minus a times r to the n plus 1 over 1 minus r. So either one of those two will do. I personally prefer this because why should I multiply by a twice when I can just multiply once? I'm going to subtract anyhow. So here I have to do one operation. In addition, let's pretend the exponent is one operation. So 1, 2, 3, 4, and then 5 versus 1, 2, 3, 4. Oh, I guess it is the same. Yeah. Anyway, I prefer this one still. But it's the same. Either way, you're going to be okay. So still in example 7, still, we want to find S sub 10, for instance. Yeah. Yep. So the formula calls for S sub 10 being, now remember, this is equal to 2, no, the first element, which is 1, plus 2, plus 4, plus 8, plus 16, 1, 2, 3, 4, 5, okay, plus 32, plus 64, plus 128, 1, 2, 3, 4, 5, 6, 7, 8, 2 more to go, 256, 512. And you can do that by adding one by one. Now, the addition is not going to be as easy as with the arithmetic sums. In the arithmetic sums, if you add the first and the last one, which is 513, that would be the same as adding the second term and the second from last one, but that's not the same. So arithmetic and geometric are quite different, very, very different. So we can add one by one, or we can use the formula. The formula calls for the first element, which is 1 minus the ratio, which is 2, to the 11th exponent over 1 minus 2. Now, multiplying by 1 does not change anything, so we can just neglect that. 1 minus, now this is the 10th element. Finding the 11th element is easy. We have to just multiply by 2. 1024 over 1 minus 2. Oh, 1 minus 2 is negative 1. So this is negative 1023 divided by negative 1. The negative simplify, and of course, negative over of course, 1023 divided by 1 is 1023. So here is the sum. If you add 1 plus 2 plus 4 plus 8 plus 16 plus 32 plus 64 plus 128 plus 256 plus 512, we are going to end up with exactly 1023. Yep. Yep. One more sequence. Um, 8. Let's say we have 1, 1/3, 1/9, 1/27, 1/81, well, etc. So the first element is 1. The next element is obtained by multiplying by 1/3. And 1/3 times 1/3 gives us this. And 1/3 times 1/9 gives us that. So the ratio is 1/3. Let's say we want to find the first 10 numbers. There's two things I want to find. Let's find A sub 10 and S sub 10. Okay, so A sub 10 will be the first element, 1 times 1/3 to the 9. That's the formula for the 10th element. And that is the same thing as 1/3 to the 9, 1/, let's see if we can do this here. So 3 times equals 2, 3, 4, 5, 6, 7, 8, 9. 19,683. There. So those elements get smaller quite dramatically, very quickly. 1/81 is small. And then the next one would be 1/243, which is really, really small. It's less than 1%. Anyway, the last term is this. If we want to add them all, this plus that, plus that, plus that, plus that, all the way down to this guy, then the answer is 1 times 1 minus 1/3 to the 11 over I'm just verifying that this makes sense. Yeah, that's correct. 1 minus 1/3. So we need to find 1/3 to the 11. So instead of doing 3 to the 9, we have to do 3 to the 11 instead. And that is 1 minus 1 over, so not 19,682. We need to multiply that by 3 more times. By 3 gives us that. By 3 gives us this number, 177,147 over 1 minus 1/3. Okay, I'm going to continue this computation here. Okay, so equals, indicating that now this is equal to what we're going to write next. This one can be written as 177,147 over 177,147 minus 1 over the same denominator. And then this 1 can be rewritten as 3/3 minus 1/3. Okay, so let's continue with this computation. So if we just same denominator, so if we just take one away, we end up with, boy, 177, 146 over 177, 147, and we're going to divide by 2/3. Now, dividing by a fraction is the same thing as multiplying by the reciprocal. So this is 177, 746 over 177, 147 multiplied by 3 over 2. And we can simplify, we can do a third of that. So those two simplify, the 3 and the denominator. Let me see. Yep, we can divide that number by 3. So those two simplify, and we end up with 59,049. And then those two simplify also. So 177, 743, 46 rather, divide by 2, and we end up with 88,873. And that's about it. Yep, so there's our fraction. As a decimal, sometimes I will ask for a decimal in this case. So divide that by 59,049, and that is the same thing as 1.505072. That's very close to 1.5, by the way. Yeah. No, but it's actually, if we keep adding more, if we were to add more elements in the sequence, this number will continue going up. So this 1.5 is a little misleading. Anyway, the answer is this. Yeah, either that or this as a decimal. Yep, yep. Okay, so practice geometric stuff. Yeah, very, very important to practice. So the next topic I want to cover in this video is changing decimals into fractions. From decimals into fractions. Yep. Every decimal number that repeats can be written as a fraction. Every decimal can be written as a fraction. Well, every decimal that repeats. So for instance, if you have, I don't know, 5.37, 37, 37, let's make an example out of this. And this would be example 8, no, example 9. Because we have a sequence that repeats, 37, and so forth, this can be always written as a decimal. Now, if there was no sequence, no repeated sequence, then we cannot do that. Only when there is a repeated sequence, even if the sequence of repeated numbers is long, you know, like 10 decimals, 10 digits, and then it repeats back to the same 10 digits in the same order and so forth, then we can find a fraction. But if there is no repetition, then we cannot do that. Yeah. Yep. So how do we go about this? There's a standard way of doing this. Let's label this as X. You can label it anything you want. So multiply by 100. So 100 x's will be, which means move the decimal point 2 places, 537 point. So the decimal point gets shifted this way, or the other way to think about it, the decimals move to the left. So be as it may, we end up with 0.37, but not this 37, 37, 37, 37, but there's an infinite number of 37, so it doesn't matter. We still have an infinite number of, even though we shift the 37, we still end up with a bunch of 37s thereafter, forever and ever and ever. Let's write x underneath again, which is 5.37, 37, 37, and so forth, and then subtract the two equations. 100x minus x, 99x. 537, well, let's do this digit by digit. 7's cancel off and we end up with 0. 3's cancel off and we end up with 0. So this happens across the board for a long time. You know, the decimals cancel each other out. 7 minus 5 is 2. And then we still have 3 and the 5. But this is a whole number. So x, which is the original number we had, is equal to 532 divided by 99. If we can simplify this fraction, we should, we must. Let me just double check, because 3 doesn't go into 532. 11, let me check that. 11 doesn't go into 532 because 11 also goes into 99. So 532 divided by 11. No, it doesn't. So this is the answer. By the way, when I say a fraction, it is implicit that we mean a fraction of whole numbers. Yeah, if you put 532 divide by 99, we're going to end up with 5.37 forever. And sure enough, we got 5.37 going on forever. So that is the way to do this. Now, you got to use judgment when you are applying this method. Okay, example 10. Let's say we have 17.88888 forever. Okay, and we want to rewrite this as a fraction. Well, as before, we label this as x. Can you multiply by 100? Yeah, actually, we could. 100x would be 1788.8888 forever. X, on the other hand, is 17.8888 forever. If we subtract the 8's cancel off, except here, so all of this is 0 and 0 thereafter. 8 minus 7 is 1. 8 minus 1 is 7. 7, 1. Interesting. So we end up with 99x equaling that. I'm trying to think. So x is 1771 divided by 99. However, I think this time we can simplify, but let me check. 1771 divided by 11, which is the one I think works. Yep, it does work. So we can divide by 11 here and end up with 9. Divide by 11 there, I just did, and we end up with 161. So this is the fraction. Now, we have to use, well, we don't have to. I didn't have to use good judgment here, but we should use good judgment. And what I mean by that is, it is overkill to multiply by 100. If we multiply just by 10, that will be sufficient to have, yeah, in fact, if you have 178.8888, if we were to multiply just by 10 and keep the 17, think about that. 178 minus 17 is 161. And then we wouldn't end up with this big number that we would have to simplify thereafter. So use the smallest number that works. That's the idea here. Having said that, okay, you know, some of the smaller numbers we can use are not that small. Let's say we have 6.123, 1, 2, 3, 1, 2, 3, forever. Okay, let's label this as X. Okay, I'm gonna do it the wrong way. I don't know if there is such a thing as wrong way. Um, you know, uh, there is trials and errors. You know, it's funny how in math, very quickly we judge ourselves to being right or being wrong. I don't judge ourselves. I mean, yeah, for purposes of assessing, coming up with a grade, I guess we do. But in general, I don't think math as right or wrong. I think of trying, exploring, trying some more. You know, it's like a basketball player when he or she misses um, a score, we don't necessarily say, "Oh, that person did the wrong thing." I don't know if I'm making myself understood. Um, you know, how come in basketball we don't say, "Oh, that person"? It's very rare that we say that person did something wrong. They just tried and it didn't. The ball didn't go through the hoop. Big deal. You just try again later. Um, but in math, we judge ourselves too quickly and we say, "Oh, we did it wrong." Wait a minute, we're trying. And if it doesn't work, then we try again. Anyway, if we multiply by 10, we end up with 61.231, 231, 231, etc. And if we try to subtract x, as we did earlier, which is 6.123, 123, 123, what we notice is that the digits don't line up. Oops, digits don't line up. So that is a failed attempt in the sense that it does not achieve the goal of getting rid of the repeating sequence of digits. See, what we're trying to do is just get rid of the digits that are repeating. And that doesn't work. So that's, again, a failed attempt. Failed attempt. But in the practice of learning anything, it doesn't have to be math, learning anything, a failed attempt is not a big deal. It's, in fact, a failed attempt is almost necessary to keep learning more. In fact, you know, when a basketball player gets a ball, let's pretend it's a new ball, you know, and that person throws the ball, even if it is a very, very a professional, you know, they may need to calibrate the ball. Maybe the ball is just slightly off, you know, a little heavier, a little lighter, a little more slippery, a little more grippy. Who knows? You know, so they might fail a couple of times, but what they are doing is they're thinking, oh, okay, this ball is different. Yeah. Give a basketball player a soccer ball, and let the basketball player, you know, try to throw the ball through a hoop. Well, this is a different ball. It's not a basketball. So they have to think, okay, I have to compensate a little bit. I have to do this or that. So they may throw once, two, three times, they may fail. But we don't think of them as failing. We're thinking, okay, they're just calibrating. They're trying to figure out the right compensation. And that's kind of what happens in a lot of the learning we do. We don't fail. We are just trying to recalibrate what we have to do. So even though I'm calling it failed attempt, In sciences, we don't mind failed attempts as much. Anyway, so multiplying by 10 doesn't work. Let's multiply by 100. So we end up with, it's not 6, but 600. So 612.312, 312, 312, etc. While x is 6.123, 123, 123, etc. Okay, again, digits don't line up. So we cannot subtract. So let's label this as a failed attempt. But again, in sciences, it's not a big deal. It's the opposite. We embraced failed attempts because we learned from them. You know, when we multiply by 10, the 1 shifted and we started with 2. When we multiply by 100, the 1 and the 2 shifted and we started with 3. So what we really need to do is multiply by 1,000. So the 1, 2, 3 shift and we start again with 1. So 1,000x is 6123, period, 1, 2, 3, 1, 2, 3, and so forth. X is 6.123, 1, 2, 3, and so forth. And so then we subtract. And because the digits do line up, 3 minus 3 is 0, 2 minus 2 is 0, 1 minus 1, 0, 3 minus 3 again, 0, 2 minus 2, 0, 1 minus 1, 0. 13 minus 6, because we borrow 1, is 7. And then we have 1, 1, 6. So x, well, this is going to be, by the way, 999x equals that. So x is 6,117 divided by 999, which we should simplify. And unfortunately, there's no way to simplify any sooner. So what we have to do is just simplify this. This is divisible by 3. Yep. So divide that by 3 and we end up with 2. Divide 11 by 3 and we end up with 3. But then there's 27, so 9. And divide that by 3 and we end up with 3, 3, 3. The only way to simplify that, let's see, 3, 3, 3 divide by 3 gives us 1, 1, 1, which is divisible by 3, 37. If 2039 is divisible by 37, then we are okay. We can simplify more. 2039 divided by 37. Nope, I did it. So this is it. So 6.123, forever is the same thing as 2039 divided by 333. Exactly. And you can double check. If you type in 2039 divided by 333, we end up with 6, 1, 2, 3, 1, 2, 3, 1, 2, 3, 1, 2, 3, and so forth. Yep. Yep. I like to give a problem in the video so that students have something to think about. So let's do this one, 12. Okay, 7.4, 1, 2, 1, 2, 1, 2. That shouldn't be too hard, but I just want to throw that in. Find the fraction. This is a little twist. This is a little different. This is a little bit of a challenge. Find the fraction, you know, whole number over whole number that produces this decimal. 7.4, 1, 2, 1, 2, 1, 2, 1, 2, 1, 2 forever. The challenge is, or what it makes this problem different is that in example 11, actually in all of the examples, Yep. The repeated sequence started right after the decimal point. 37, 37, 37, right after. 8, 8, 8. Right after. 1, 2, 3, 1, 2, 3, 1, 2, 3. In this example, this repeated sequence doesn't start right after the decimal point. It starts later. 4, 1, 2, 1, 2, 1, 2. So how do we handle this? Okay. So post, if you can, post the answer. And that's it. We're going to stop the video here.